Hello, everyone. I'm going to talk about the basics of quantum physics in this PowerPoint presentation for you. So I have prepared like a lecture of, let's say, like 30 to 40 minutes for you to become familiar with uh, everything about the quantum physics and what I thought that you need to know in this course. But please refer to your textbook and study more about it if you want to understand the deeper meaning of quantum physics. Also, I have brought some sample examples of the questions that might show up on your exam, because if you have seen in my announcement, I told you that you will have some conceptual questions about this chapter, which is, I believe, chapter 30 and 31 on your book. But I never gave you like any example. So if you stay with me, you're gonna see what type of examples I meant. All right. So before we even start talking about quantum physics, let's just watch this video from a very brilliant colleagues of mine that talks about like how to simply um, talk about quantum physics, or what is quantum physics. When we say quantum, what is exactly we're talking about.
So, have you ever had this experience? You're having a chat with someone, and they're telling you something about a subject they're very interested in or they know a lot about, and you're following along, and then at some stage you realize you kind of lost the thread of what they're saying, and then you're standing there and you realize you've got absolutely no idea what they're talking about. I had this recently with a friend who knows a lot about investing, and it's something I don't know a huge amount about, but it's very important, very useful information. When he started talking about kind of diversified investment portfolio, blah, and unfortunately I went away with no useful information. So I think it's a situation we all are familiar with, and fortunately, there's things you can do to improve this situation, which is what I'm going to talk about today. So I'm a scientist. I work in the area of quantum physics. And so I've been on both sides of this kind of interaction. I've both been the guy explaining the very complicated material to someone, but I've also been on the receiving end of lots of very kind of intense scientific discussions with my colleagues. And when this kind of breakdown of communication happens, I've noticed something interesting, which is that as a person who's stopped understanding, you feel kind of guilty about it. But if you think about it, this is completely wrong. It's the wrong way around, because at that point in time, there's literally nothing you can do to understand better. But there is something that the other person can do to help you understand by finding a better way of explaining what they're talking about. And so during my experience in science, I found that the only way to survive was to kind of have the courage to politely stop the person who is explaining, say, "I'm sorry, I don't understand what you're saying," and then try and go back and start off from where I'd lost the thread. And it does take a bit of courage to do this, because you're kind of admitting that you don't know, the subject matter. But I think that's okay. And in fact, my fears were completely unwarranted. Generally people respect you if you care that much about, knowing the right information, or care about understanding properly. So I think we should never, ever feel bad about not knowing something. And we should never feel bad about asking questions. So I do a lot of science communication, and science really has this communication issue with it because generally the subject matter is very complex. And you might know scientists are always complaining about how their research is being misrepresented by the media. Like, drinking wine cures cancer. It totally doesn't, by the way. But on the other hand, you can kind of understand how journalists will maybe oversimplify things or get things wrong, because to explain cutting-edge research, you kind of need a PhD in the subject beforehand. And it's not something we can expect, the media journalists to have in all the different scientific disciplines. So I think the world would be very well served by a whole load of people who are really, really good at science communication. People who understand the science but can also explain it in a way that the general public can understand. And this is important for many reasons, but one reason is you might know that just about all the science research that goes on around the world is publicly funded. So it would be nice if the general public could actually understand the work that their money is going towards. But for me, the even more important reason that science communication is good is because it's all so interesting. The research going on is so fascinating, it would be nice if people could access it. Take my field, for example, quantum physics. I find quantum physics to be a deeply interesting subject, but it's one that gets this reputation of being incredibly difficult. And that's fair. It gets complicated when you get down into the details. But it doesn't mean you can't talk about it at all. So let me get a show of hands. So put your hand up if you don't know what quantum physics is. And if you don't feel bad about it. Raise your hand. Own your ignorance. It's totally fine. Okay, right. So quantum physics is the description of the smallest things in our universe. So if you zoom right down, smaller than cells, down to the scale of molecules, atoms, and things atoms are made of, subatomic particles, protons, neutrons, electrons. And it describes how they all work and also how they interact with light. And the interesting thing about quantum physics is it's like the fundamental rules of the universe, and yet the things that happen there are so very strange. So I'll tell you a few of the phenomena that go on in quantum physics. One you might have heard of is called particle-wave duality. So you can imagine all these subatomic particles, these protons, neutrons, electrons, like little bouncy balls, kind of bouncing around, bouncing off each other. But sometimes you have to treat them as like spread out waves. And they kind of do both at the same time, which is hard for us to imagine. So I'll paint a picture. Imagine dropping one of these bouncy balls into like a pond of water. The ball would disappear, and then you get these ripples going out over the surface. Now imagine one of the ripples hits, say, a stick. All of the ripples on the surface disappear, and by that stick, suddenly a bouncy ball pops out again. That's kind of strange for us to think about, right? But this is the kind of behavior that goes on in the subatomic realm all the time. Another phenomena you might have heard is called quantum tunneling. So imagine I'm throwing one of these bouncy balls against a window. So it'd be like throw, bounce, catch. Throw, bounce, catch. Throw. It's gone completely through the window. It's not smashed it. It's not interacted with it at all. It's just suddenly on the other side of the window and you can see it flying away. If we saw that, we'd think it was crazy, right? But this goes on at the subatomic realm all the time. In fact, it's the only reason we exist. So you might know that in the sun, the way it generates energy is through nuclear fusion. And nuclear fusion is when two hydrogen atoms come together and the protons in their nucleus bounce off each other. Now, if it wasn't for quantum tunneling, they'd bounce off each other and nothing would happen. What actually happens is they quantum tunnel into each other. And that's what lets them fuse and release the sunlight. And without sunlight, we wouldn't exist. So we can thank quantum tunneling for our existence. Another phenomena is called superposition. It's a very fancy word, but all it means is something that can do opposite things at the same time. So, for example, I can spin around one way, I can spin around the other way, but what would it look like for me to spin around in both directions at the same time? We can't do that. We can't imagine that. But this is what these subatomic particles do all the time. And in fact, we can kind of do it. At least bits of us can. So if you've ever been in an MRI machine, what an MRI machine does is it finds all of the hydrogen atoms in your body and makes them spin around in both directions at the same time in this superposition. This is what allows us to see inside people's bodies. So it's interesting that all of this physics seems so kind of abstract and remote from our everyday experience. And yet it's happening inside our bodies. We're made of quantum stuff, so it's happening everywhere around us. And it's not just MRI machines that we use like quantum physics for. There's been a whole host of other technologies that come about because of our understanding of quantum physics. So one of those is our understanding of silicon allowed us to invent the silicon chip, which is in every single computer in the world. So the entire computing infrastructure of the world exists because of our understanding of quantum physics. And it's in other things like lasers, they're quite useful, and nuclear power plants. And there's this other soundbite you might have heard about quantum physics, is that no one really understands quantum physics. Well, that's actually wrong. We do understand quantum physics very well, and you'd kind of hope that we did if it forms the technology of MRI machines or nuclear power stations. What they mean when they say that is that when we try and picture in our head something that can be both a particle and a wave at the same time, or something can spin around in two directions at the same time, we find it very hard to picture that in our heads, but we can describe it all very well using mathematics. So it's fascinating that something can be so counterintuitive on one hand, but yet can be so practically useful on the other. So I really enjoy explaining science to people.
Okay, so let's just stop this video here because the rest of it is for his book. And let's go back to the quantum physics. All right, so the first thing that quantum physics talks about is that light has aspects of both waves and particles. All right, so what he was talking about when he said wave-particle duality is like the most well-known aspect of quantum physics. Okay, and then we are here talking about the three models for the light. Now, the ray model is the first model that you can see here, and it says that light travels in straight lines. So this is how we explain mirrors and lenses. The second one is the wave model, and you can see the schematic here, that describes how light waves spread out and how superposition of multiple light waves causes interference. Remember that we talked about interference and diffraction a lot. So what helped us explain interference and diffraction is the wave model. And the third model for light is the photon model. Now, this is the important part of quantum physics. The photon model says that in the quantum world, light behaves like neither a wave nor a particle. Instead, light consists of photons that have both wave-like and particle-like properties. Okay, so a light can be both wave and both particle, but when is it behaving like a particle, when is it behaving like a wave, is something that we need to first understand all the quantum basics. All right, so what we know is that in an atom the electron orbits the nucleus in much the same way that the earth orbits the sun. The only difference is that the electron is held by the electric force, but the earth is held with a gravitational force. Now, in quantum physics, we must also think of the electron as having some of the properties of a wave. So in quantum physics, electron is not a particle anymore, or it is a particle, but it has some properties of the wave too. Now, if electron has some properties of the wave, then the frequency of such a wave is given by the first key equation of quantum physics, what we call the Einstein equation. Okay, so Einstein equation that you can see here, E equals to hf, relates the energy of such a wave, meaning the wave of an electron, to its frequency. Now, E is the energy, phi is the frequency, and h is something that we call Planck's constant. So it is taken after Max Planck, the scientist here. So frequency is measured in hertz, which is like similar to all the frequencies that you know. It's the number of cycles per second. E is measured in joules. And then the Planck's constant is 6 times 10 to the power of negative 34. Okay, so a typical atomic energy is about 1 electron volts. And we know that 1 electron volts is equal to 1.6 times 10 to the power of negative 19 joules. Now, according to Einstein equation, E equals to hf, and if I want to find frequency, I need to divide E by h. So let's go ahead and divide the typical atomic energy by the Planck's constant, and we get 2.7 times 10 to the power of 14 hertz. So this is the frequency of electron wave. This means that electron waves oscillate with extremely high frequency. It's the scale of 10 to the power of 14. Maybe that is why, or not maybe, but for sure, that is why we never notice them, because they oscillate so fast that our body cannot perceive such oscillation. Another important topic in quantum physics is the quantized energy, and that is how we even use the name quantum, right? It means that the energy is quantized. In an atom, the wave packet is usually longer than the circumference. Okay, so imagine this situation. You have an electron that is orbiting an atom. It's orbiting around a nucleus. Now, because the wave packet of this electron is very long, longer than the circumference of the orbit, the electron wave can run into its own tail. So it is so long that the head will reach the tail. Now, because it is a wave, these two can cancel itself out. Now, if they cancel itself out, it means that there is no wave there, so there is no electron there. So if the electron is orbiting the nucleus, the only possible orbits for that electron are those where after an orbit the wave does not cancel. Okay, so again, imagine a nucleus and there is a wave going around an orbit around the nucleus, but the wave is too long that the head reaches the tail and it can cancel each other. If this happens, it means that there can't be anything in that orbit. So the only possible orbits where electrons can exist are those orbits that the wave does not cancel. So this means that only certain frequencies are allowed. Now, according to Einstein equation, frequency is related to energy. So if only certain frequencies are allowed, this means that only certain energies are allowed. So this is stated as the electron energy is quantized. For example, look at this figure here. This is a schematic of a hydrogen atom. Now, in hydrogen atom, the allowed energies are 13.6 electron volts, 3.4 electron volts, 1.5 electron volts, 0.85 electron volts, and so on. Okay, so these are the energies that do not lead to self-cancellation of the wave of the electron. This means that electron can be anywhere in this orbit or in n equals to 2 in these three orbits here, when n becomes equals to 3 in only these 3 orbits here that is not even a circle. But anywhere between these two, it cannot exist. Anywhere between these two, it cannot exist. Okay, so there are a lot of allowed energies. How we know what energy is allowed? We can drag it from this equation, this formula. This is called Bohr formula, because Bohr was the scientist that gave this model about the hydrogen atom. So this is a part of chapter 31 on your book that talks about the Bohr model for the hydrogen atom. So the energies that are allowed according to Bohr formula is 13.6 divided by n squared. Okay, so kinetic energy of electron in the energy levels. Now this n is just an integer. It can be 1, 2, 3, go to infinity. Now the energy that we get from this formula has the unit of electron volt, because this 13.6 is in electron volt. For example, if you put n equals to 1 here, then you get 13.6. If you put n equals to 2 here, then you get 3.4, and so on. Notice that there are infinite number of allowed energies, but also there are many energies that are not allowed. They are forbidden. And those are the energy levels that are between the allowed ones. So if on your exam I give you a question that says which of the following is not an allowed energy level in a hydrogen atom, and then you have bunches of numbers, you should see which one is not obeying the energy that comes from this equation. Now remind or recall this fact that this n can be any number, that was a big mistake, any integer. But it cannot be, for example, 1.5, 2.3. It should be 1, 2, 3, 4, 5, and so on. All right, so no electron can orbit the nucleus of hydrogen atom unless its kinetic energy matches one from the Bohr formula. And then although the energies of orbiting electrons are always quantized, an electron that is moving through empty space in a straight line can have any kinetic energy. So we have two types of electrons. The ones that are bound to move in an orbit around the nucleus, which only can have quantized energy because they have quantized frequency, and the ones that are moving through empty space in a line. So those, the ones that are moving through empty space, they don't have any restriction. We don't have the Bohr condition for them. So we call them free electron because they are free. Their energy is not quantized. Okay, let's talk about hydrogen molecule collides with another molecule and see what happens in the quantum world. So when one hydrogen molecule collides with another, it can knock the electron from one allowed orbit to another one allowed orbit that has a greater energy. So this collision can alter the energy stored in an atom. But again, pay attention that it's only from one allowed energy to another allowed energy. Now, if this collision increases the energy of the electron, we say that the atom is excited, right? Because the electron becomes more energetic. Or the electron is in an excited orbit. So the electron that is in an excited orbit can lose this energy and fall back into the original orbit by emitting an electromagnetic wave that carries off the energy difference. So you excite an electron by giving it some sort of energy. For example, via collision, it goes to an excited state and then falls back and radiates an electromagnetic wave that has the energy difference between those two status. Okay, in quantum language, we say that the electron changes its orbit and emits a light wave. This is called quantum leap. Okay, so if the energy difference between the two orbits is E, then the energy that is carried off by the light wave that comes out of it has a frequency that can again be calculated with Einstein equation. So the frequency of the light that is emitted is related to the energy or the difference between the energy of those two levels or two orbits with Planck's constant. Since the frequency of the emitted light is quantized too, because the energy is of course quantized, this means that the emitted light has only certain color, right? Because the frequency is color. So this means that the color of the emitted light is also quantized and only certain colors are emitted. For example, if you put the light from the hot hydrogen gas through a prism to separate out the colors instead of a continuous spectrum, which is what we get from the sun, we only see a few colors that are present in that emission spectrum. Let's take a look at these pictures here. So the above one, this picture shows the spectrum of hydrogen. Now you see that there are only some certain colors emitted when hydrogen gas is heated. But then the picture that is on the bottom, that is the spectrum that we get from the sun, and you see how continuous this spectrum is. Now, these spectral lines are actually good ways to identify an element from the light the element emits. Okay, so this is called spectral fingerprinting. Fingerprinting. This means that if you have a gas and then you make it very hot, then it starts to emit. Okay, and if that emits, for example, the certain colors that we know it's the color for hydrogen, so that means that the gas has the hydrogen in it. But if you heat the gas to a very, very high temperatures, for example, the temperature that you have on the surface of the sun, then the electrons get that extra energy that they can get knocked off the atom. So they are not bound to go around the orbit in the atom. Then we'll have separate protons and electrons, and that is the gas that we call a plasma, right? So when this happens, the electrons are no longer circling the protons, their orbits are no longer quantized, and they can have any energy. So this is what happens inside the sun. The electrons are not bound to the nucleus anymore. The electrons are free electrons because we have a plasma there. So that is why instead of just seeing some specific lines of colors, you have a continuous spectrum for the sun. So in this case, we say that the spectrum is continuum. Okay, so this is here a very beautiful demo that shows the spectral lines of some of the gases.